Good morning, my friends. If you can hear me, type in good morning. Good morning, Sonia. Hey, John, good morning. Stephen, good morning. Julia, Andrew, Ariana, good morning. Owen, Hannah, Sweta, nice to have you join us. My friends, we have an insane subject matter today. We're doing cosmology and metaphysics, but before we do that, I'll talk about the exam. So this is our last class, and you've got your final exam, and I always want to send you in knowing what to expect. So I'll tell you what to expect, and I'll answer any questions you might have. So once we've done that, then we can move on to our subject matter for today. So cosmology and metaphysics, and we'll see. I'm going to tell you a story on basically what drove Peirce to say the things he said. It mainly has to do with Darwin. And so Darwinism, according to Peirce, and I think he's correct, changes everything. And most people agree that that changed everything, but it actually was more revolutionary. Darwin's ideas are more revolutionary than most people realize, and we'll see why today. And this led Peirce to talk about the universe being driven by chance and habit taking, which is a surprising view, but makes a remarkable amount of sense. And so what we're going to do today is I'm going to make it make sense for you, and we're going to do that with various activities. So today, it's like, one of those lab experiments that you can do in your kitchen. We're going to build a universe. We're going to build two toy universes, two model universes. First, we're going to build a small model universe to make some physical laws. So I'll give you a recipe for baking the laws of physics from your own home in a petri dish, if you will. And then also we'll do the same thing to create life. We're going to build a toy universe and start making little creatures. And so it's going to be fun. And the point of that is to make Peirce's ideas look more sensible than they might at first appear. And then after that, we'll look at our Peirce packet. And I think if I would have done the Peirce packet on its own at first, although Peirce writes well and argues quite persuasively, it takes a little getting used to. So his cosmology and metaphysics is considered to be either completely crazy or way ahead of its time. And I'll let you decide. I'm obviously going to give him the most charitable presentation possible. And I'm going to say that his cosmology is way ahead of its time and it's actually on the right track. So that's what I'm going to do today. And I've worked a lot to try to make it happen, right? To try to make it all make sense. But first, we'll talk about the exam. So is that good, everyone? Is everyone good to go? Does that sound like a good way to spend our time? If you're good to go, tell me good to go. Stretch. Have my first sip of coffee. I'm going to confess that I want this semester to end. It's not that I don't love all of y'all, but I'm tired. It's I need, not that it's going to be a break once it ends. There's more work, but I'm starting to feel the levels of fatigue are starting to kink in. But I love this course. This is my baby. This is my little prize, my pride and joy. And so I really want to give it everything I got today. Then I can collapse with exhaustion. Let's talk about exams. All right. So if you go to our week-by-week breakdown, right, and even our grading, you know here that we have an exam. The final exam is worth 30%. It's held on August the 19th. Be mindful that it's from 8:30 a.m. to 11:30 a.m. So it's scheduled by the university. That means you got to go to bed earlier and you got to plan for this. The exam is going to have the following structure. You're going to have 5 questions, so 5Q, right, times 6% each, right? 5 questions times 6% each. And I know what's probably on your mind has to do with, let's say, the logic and the existential graphs. There will be no questions having to do with existential graphs directly. All right, so you're going to have 5 questions. The 5 questions are going to be about the stuff we did since the midterm, although Peirce's philosophy is a system, so there's a sense in which all of these ideas are interconnected. This this final exam is going to be on everything here. So that's philosophy of logic. The diagrammatic logic stuff that we did, you've had 10% in the quiz is going for that. So I'm satisfied that you tried your hand at it, but I'm mainly going to use the logic stuff to inform your understanding of the philosophy of logic ideas. Remember that reading in philosophy of logic on its own would have been a bit cryptic, but when you finally spent some time practicing the existential graphs, you can see what he's talking about and when he's talking about his conception of what logic ought to be, right? So you're not going to have any questions on that per se. So if I was to redo this a little bit, it's probably like this, right? You'll be examined on philosophy of logic, you'll be examined on philosophy of science, and you'll be examined on cosmology and metaphysics, which is what we're doing today. That's what the final exam is going to be on, right? With the understanding that this stuff that we did here, right, this logic stuff, this is what makes the philosophy of logic make sense. If you've now been exposed, all right? So is that fine, everyone? I know some people must have been worrying, oh my God, are we going to have to do some derivations? You will not have to. Is that clear? If that's clear, type in clear. If you have a question, ask your question. And the reason for that is, and Andrew writes, is there a choice of which ones to do, like the midterm? Yeah, all in all, you'll have 5 questions, and I'll give you 5 questions and only 5 questions. So you won't be able to choose though. So you'll have 5 questions and 5 questions, Andrew. Does that answer your question? There'll be no wiggle room for this one. Yeah. And the reason why I'm not requiring you to do existential graphs per se is not that they're not fun or they're not worthwhile, which I think they are. It's just that I genuinely, for an online course, don't know how to do it. I've done this in the past, and I short of the things I did for the quizzes, right, which are just little drills basically to understand the permissions. I don't trust you to write out your derivations and to draw them out. Your handwriting is probably going to be horrendous, and the logistics of having to upload those images and whatnot are so complicated. It's a complete nightmare. So we're just not going to do that. If this was a live class, I'd include one question where I'd probably just, throw a small argument at you to see if you can handle it with the tools of existential graphs. But I think it was worthwhile to do all of that because it allowed you to see the philosophy of logic in a new light. Like when Peirce talks about all this stuff about how he's going to use diagrammatic signs and so on, and it has to do with working together, diagrammatic reasoning, that whole spiel. It makes sense only when you see it, and appropriately enough, because you can't just use symbols to convey what icons say, right? The sort of information that icons convey, if all we did was a reading in English and we had no diagrams whatsoever, you would have failed to see what he's talking about. It was great to do that, and you were graded for 10%. It did amount to 1/10 of your final grade, so I'm satisfied with that. But logistically, it's a little more complicated for an exam. I have to say, though, it was an absolute joy to do that together a few weeks back when we were working on this, and we would put on our VR gear and we'd work together. That worked out amazing. With Big Blue Button, that worked out amazing because this is the first time I teach this Peirce class online. That was really, really cool. What did you think, folks, when we were able to work together on the screen and share screen? You share my opinion that was a really cool thing? I thought it was really neat. Like, what did you think? Because Reese says it was very cool, and some people were brave enough to jump in, yeah, and it helped to make sense of it. And what I like was that we really were working as a group, as a community of inquiry, yeah. And Reese says I haven't had the chance to do that in other online classes. This is one situation where even if I was teaching face to face, I'd like it. Well, we could do it on a board, but this is one situation where I felt like the online format served us well. Yeah, Ariana says it was fun. Yeah, and I got a chance to try it. Agreed. Read online. Owen says it was really fun, actually engaging. Online has pretty much sucked otherwise. Yeah, I mean, hopefully you say otherwise for other courses, not just otherwise except for that, Owen, right? The rest of my stuff's still pretty cool, I hope, right, Owen? Because I'm trying to put visuals and make it fun, and we did lots of really cool stuff in this class, right? So, yeah. I'm hoping. Okay, cool. Because Papa Bear's working really, really hard, and today's no exception. Today I'm gonna have to be quite a DJ and work on different platforms here, because we're gonna do a lot of really neat stuff. And today we're gonna learn about a bunch of new words: cynicism, tychism, ananchism, agapism, panpsychism. Peirce had a tendency. I mean, some of these aren't his, but had a tendency of coining new words because he felt he was developing new concepts, basically, for which there were no precedents. And so hopefully this will make some sense. And the spelling changed a lot often. So don't be surprised if you look some of this stuff up, especially in the Peirce dictionary. There's an online Peirce dictionary. Yes, that's a thing. And there's a link on Moodle for it. It's called the Commons Dictionary. And commons is itself a word that Peirce invented for the idea of a calm mind, a combined mind, that overlap between your mind and mine. Peirce literally thought that was a thing in itself, a calm mind, a combined mind, if you will. Anyways, there's a dictionary, and you'll see the spelling changes often, but we'll understand what these words mean. They're going to look less mysterious at the end of this class. So final exam, August 19th, 8:30 a.m., last 3 hours. You're going to have 5 questions. You don't get to choose. They're worth 6% each. If they're worth 6% each, that means they're graded out of 6. There'll be 3 varieties of pass, 4, 5, and 6 out of 6. And 3 varieties of fail, 1, 2, and 3 out of 6. If you show up and you write something, you're guaranteed to get 1 out of 6, so just show up. And if you answer the question correctly, it's a variety of pass. If you answer the answer incorrectly, it's a variety of fail. You have about a half page to answer each question, and aim for beautiful quality, you know, and no copy pasting under any sort. And that's it. Any other further questions about the final exam? If everything's clear, type in clear. If you have a question, ask your question. And do be mindful that when I will be talking about philosophy of logic, I will be expecting you to be able to draw on examples from. So all of this stuff, by the way, just as a reminder, you know, you're supposed to know what these things mean. And if they serve you if they advance your answer, you know, as an example of what the heck you're talking about, put them in, right? It's not like I'm saying you ought not to refer to these things. Those are still legit, but you just explain them in language, in English, right? Not in diagrams. All right, well, it looks like everyone's good to go, that they know what they're doing. Let's start this stuff. Let's start our cosmology and metaphysics. Darwinism changes everything. What does Darwinism change? It changes the standard picture. And the standard picture is this. I'm going to show you a video. This is something I grabbed off YouTube, and it gives you a picture of what I would call the orthodox scientific view. At any rate, depends. If you keep working up the echelons of science, most scientists actually might start agreeing with Peirce on a lot of things. But this is the standard view. So can everyone see some guy in a lab coat, and it says "Boring Science: The Clockwork Universe"? Cool. I'm going to play that. And this is going to be an account of the universe that, you know, most folks are taught in school, that you were probably taught in school, and that most, you know, educated people think is the way you ought to understand reality, right? So let's have a look.
Randomness, it turns out, does not exist. Okay, so to begin with, first you need to know that once upon a time there was a man by the name of Isaac Newton who was so extraordinarily smart that he had to hold his brains in his hair, and he came up with classical physics, or what we call Newton's laws of motion. Now, Newton's first law states that an object in motion will stay in motion until acted upon by an outside force, and an object at rest will stay at rest until acted upon by an outside force. Now, that initially seems somewhat straightforward, but it has some pretty far-reaching implications. Basically, under Newtonian physics, it's helpful to think of the universe as a sort of massive machine, where every object in the universe, in motion or otherwise, is in that state as a result of all of the different forces acting upon it. Let's go back to our dice toss. Now, to the human observer, the results of the dice toss seem completely and totally random. But that's only because we don't know all of the input forces acting upon the die at that time. Let's break it down. Now, when the die is cast, it is initially met with the upward force of my thumb. However, it is also being affected by Earth's gravity pulling it back down. There's also air resistance and wind, and by Newton's law of universal gravitation, it's also being pulled on by the gravity of every other object in the universe to varying degrees. And that's not to mention the near infinite number of other unknown forces acting upon the die at any given time. There are so many forces affecting the way the die lands that it is far too complex for us to predict the outcome. So, to the human observer, we call this phenomenon randomness. But it's important to note there is nothing random about it. A die cast in the exact same way, with the exact same forces acting on it, will land in the exact same way every time. And that's pretty cool. What this means is that every object in the universe, from the dust floating around your room to the stars in the sky, are where they are as the result of the infinite number of forces acting upon them. Or in other words, everything is nothing more or less than the result of all of the causes that came before it, and all of those causes had causes, and those causes before them had causes, etc., ad infinitum. We call this clockwork universe theory, and also Newtonian determinism, and also mechanism. It's got a lot of names. His friends just call him Frank. It's a lot easier. Now, Frank gets really interesting when you apply him to human beings. Classical physics tells us that every object in the universe acts as the result of all of the forces that came before it. And as much as we'd like to deny it, human beings are a part of the universe. We're no exception. When you say the word I, you're probably not referring to your arms or your legs or your kidneys or your spine. What you're referring to is everything going on up here. You're referring to the symbiosis of all of the different neurons in your brain all firing at once, making decisions and choices and reminding you to breathe. Well, all of those neurons in your head are firing in precisely the order that they are for the exact same reasons that the Earth orbits the sun and the die falls the way it does. It is the culmination of all of the forces that came before it. Everything that has ever happened and everything that ever will happen has been set in a perfect and unbreakable sequence of causes and effects. Time is set in place.
So that, my friends, is the standard view of the universe that you're probably taking for granted, and also a lot of philosophical debates. Have you ever seen this in a philosophy course before? This worldview? Yeah. Andrew mentions free will. One says he's never heard of this, but this is basically the view that is called determinism, right? Determinism is the view that, like the video says, like the universe is one big clock, right? And it's all working according to the fundamental physical laws. And often when this comes up on our radar in philosophy courses, it's because this raises interesting questions about free will. Because on this picture, clearly we can't have free will. Everything's determined, right? What you're going to have for breakfast, on this day, 20 years from now, technically I could predict that if I knew the current position of all the particles in the universe, and I knew the basic fundamental laws governing their motion. I could determine what you're going to have for breakfast on this day, 20 years from now, on this date, right? And so this is, for philosophers, this is a source of worry, because then they start worrying about free will, moral responsibility. We're not going to be concerned with those questions. We're mainly going to be concerned with, is this even right? And Peirce thought this was wrong. This worldview that you've just seen is wrong. And it's wrong not for the usual reasons. It's not wrong because it doesn't leave room for free will. It's not wrong for any of those reasons. It's wrong because it conflicts, Peirce held, and I would agree, it conflicts with Darwinian theory. Now, if you learn biology, if you've taken biology, who's taken biology before? Type yes if you've taken biology. No if you haven't. Just to get a sense, a couple people have taken biology before. If you take biology and you read a biology textbook, so this is a biology textbook, you'll learn about evolution. Darwin is to biology what Einstein and Newton are to physics. I mean, he's a giant. And he, along with Alfred Russel Wallace, by the way, who never gets enough love, and I think is actually the originator of all these ideas, developed something called the theory of evolution. And evolution is animated by four fundamental forces. So here's a page from a open access textbook. We're talking about the forces of evolution. Today we recognize that evolution takes place through a combination of mechanisms: mutation, genetic drift, gene flow, and natural selection. These mechanisms are called the forces of evolution, and together they account for all the genotypic variation observed in the world today. Keep in mind that each of these forces was first defined and then tested and retested through the experimental work of the many scientists who contributed to the modern synthesis. And the modern synthesis is taking what we know about DNA and combining it with evolutionary theory, right? So the four fundamental forces of evolution, just to recap, right here they are. Let me underline them in green over here, right? Mutation. Oh, that's probably a little, let me zoom in a little bit because that's probably a bit small. Here we go. See if I can scroll that over here, right? Mutation, that's one of them over here. Genetic drift, gene flow, I won't go into those two, right? And basically when populations are separated and when they're reintroduced to one another, and also natural selection. And most people understand natural selection, but natural selection only works if there's a variation among the population. So if the individuals in a certain population, different organisms have different traits, then the environmental pressures are going to start selecting for certain traits that are going to be beneficial or harmful to them. But that only works if there's variability, and the variability comes from mutation. And actually, if you want to spell it out, the full way of talking about this force, if you want to be strict, and especially if you want to be Peircean about it, right, it would be random genetic mutation, right? The genetic part is not a part that Peirce could have known of. That would be the full way of unpacking the word mutation here. because he wasn't aware of genetics and so on. This is before his time. But the random part is what causes a lot of problems, and it doesn't seem to fit quite well in the picture of the universe that we saw. So let's unpack mutation a little bit. Let's keep reading this textbook to see what a standard biology textbook says about mutation. The first force of evolution we will discuss is mutation, and for good reason. Mutation is the original source of all of the genetic variation found in every living thing. Let's try again to imagine all the way back in time to the very first single-celled organism floating in the Earth's primordial sea. Based on what we observe in simple single-celled organisms today, that organism probably spent its lifetime absorbing nutrients and dividing to produce cloned copies of itself. While the numbers of individuals in that population would have grown, as long as the environment was favorable, nothing would have changed in that perfectly cloned population. There would not have been variety among the individuals. It was only through a copying error, the introduction of a mutation or change in the genetic code, that each new allele was introduced into the population. So just a feature that is noticeable at a macroscopic scale. When we think of genetic mutation, we often think of deleterious mutations, the ones associated with negative effects such as the beginnings of cancers and heritable disorders. The fact is, though, that every genetic adaptation that has helped our ancestors survive since the dawn of life is directly due to a beneficial mutation, a changes in the DNA that provide some sort of advantage to a given population at a particular moment in time. For example, a beneficial mutation allowed Chihuahuas and other tropical adapted dog breeds to have much thinner fur coats than their cold-adapted cousins, the northern wolves, Malamutes, and Huskies. So if you're like me and you're a fan of the X-Men, you've heard of mutations, right? And mutations can be cool, right? Because if you think about, like, if I had Wolverine's claws, well, that wasn't actually, well, his claws, according to the movies, they were a mutation. They came out as bones, right? But if I had a mutation of that sort, I'd clearly be much better suited to survive, right? And if I passed that on to my kids, they'd become the top dogs in no time, right? So all my kids would have claws, and if they had a fight in the schoolyard, they'd kick some serious butt, right? And draw blood, you know? You're much better suited with certain mutations. Other mutations could make you not well suited, and then you would die. And that's the full story. But in order for the selection pressures, that is the environment around you, to start favoring or not favoring certain traits, you have to have a nice diversity in the pack of cards, if you will, right? And so I'm going to show you a video now that explains this. And the important part when you think about this is, notice there's a moment there in this video where the mutations happen, and ask yourself, is this random or is this determined, right? Because obviously if it's random, then that would tell against the clockwork picture of the universe that we just saw. So let's do a little bit of Biology 101. Let's watch a short video on mutation. Let's see if we can see that. Can everyone see someone sleeping in a bed with a door on the side? Like a hospital room cartoon or something like that. Cool. All right, so this video is just a little over 4 minutes, so pay attention. And this is a nice summary, very accessible, because this is not a biology course, but we do want to have some basics in biology to understand what we're talking about when we're talking about random genetic mutation. And as we've just seen, that's crucial for natural selection to do its work.
Aha, here's our patient. The patient has received all known antibiotic treatments to no effect. In conclusion, either he is not ill, or we have a new strain of microbes.
Or this could even just be a case of resistance to antibiotics. Let me explain. When the body is infected by bacteria, it attempts to defend itself in several ways, by increasing its temperature, but mainly by using its immune system. As soon as a foreign body enters the organism, it's detected straight away and alarm bells ring. Lots of white blood cells come along to identify the culprits and get rid of them. But sometimes these defenses are overwhelmed by bacteria. That's when the illness really begins. Luckily, since antibiotics were discovered, we can help patients protect themselves. These drugs destroy most bacteria or create a hostile environment for them. Antibiotics soon became a quick fix solution. For the slightest scratch, a course of antibiotics. It was so effective in preventing infections from developing that the use of antibiotics increased. They became widely used to treat battery-farmed poultry and pigs. But before long, the illness returns. And antibiotic treatments suddenly stop working. What happened? Well, before bacterial cells divide, they duplicate their genetic material. This material is composed of DNA. Portions of the long molecule can hold precise information on the activity and development of the bacteria. These portions are what we call genes. Each gene is composed of a sequence of 4 elements, called nucleotides, of which 2 are always matched in pairs because they're complementary. As DNA is copied very rapidly, errors in the copy frequently occur.
So notice here, as DNA is copied, errors frequently occur. So think in terms of how we've been talking about how errors are important in Peirce's theory of knowledge, in his epistemology, for what it means for knowledge to grow. Here we have errors in retranscription of the DNA, and that's what's going to give rise to mutations. So as these chains are being reproduced, they're mismatched, if you will, occasionally. And then we have to ask ourselves the question, is that determined or random?
These errors are called mutations. Most of the time, these mutations are of no consequence, but sometimes they can be harmful to the bacteria. However, with such a high number of mutations, some of these copy errors can result in resistance to antibiotics. When in contact with the antibiotic, the resistant bacteria will be the only ones to survive. In fact, the drug will have chosen the resistant strain. And then, since there is no longer any competition for food, the bacteria can multiply very fast. It's exactly like natural selection. Individuals with the most favorable characteristics reproduce more than the others.
Notice here the chameleon is only eating the white bugs that they can see. There's these other butterflies that look just like the tree, ironically, because that's a chameleon and they tend to camouflage, so he can't spot them and he's not eating them. So notice they have a certain trait that proves advantageous. They're able to hide and they survive, whereas all the white ones get killed.
Individuals with the most favorable characteristics reproduce more than the others and will be able to continue to evolve. Indeed, with antibiotics, we are reproducing what nature did 4 billion years ago that led to the evolution of species.
Well, miss, are you demonstrating here that the patient is suffering from acute Darwinitis?
You could say that.
So there you have it, my friends. This is in the news right now, right? Think about the idea of variance. Was this helpful? Did you like that video? COVID variants, right? Resistant strains. That only happens if there's mutation. Yeah, mutation is the Delta variant. And, you know, unless you wipe everything out in one go, which is almost impossible, you're just going to wipe out certain things and you'll have a freak aberration. And it only takes one freak aberration to not be wiped out. And then all of a sudden it turns out that their freak aberration proves advantageous and they start reproducing, right? And that's what you have. Now, the question is, we have to have variability in order for natural selection to do its work, right? There has to be enough variation in order for a species to survive, each member of the species can't be uniform. Like, for instance, imagine, I don't know, that let's give us a silly example, right? Imagine this is all of humanity, right? And we're all above 5 foot tall, let's say, right? All of us, all of humans, this is really silly, right? But just to give you an example, we're all above 5 foot tall. Some are taller still, right? There's really, really tall people. So you can imagine there's still variability, but we're all above 5 foot tall. Let's say the cutoff point for 5 is over here, right? And then, I don't know, go with me on this. Some flying saucer comes by and it's shaped like a spinning saw, and it goes over here and it hovers just exactly at 5 feet above the ground, and it just goes around hacking everything in its way. What happens to the human species? Let's say that small population, everyone was over 5 foot tall. The UFO flying saucer thing came and sliced everything. The species is gone. The species is gone. Everyone's dead, right? Because that feature of being tall did not prove advantageous. It's been selected against, to use the language of evolutionary theory. But what if there was some freak, right? Some person who's very different, and they were, let's say, very short. They were under 5 feet tall. What would happen to that person? The very short person, or a very couple of short people. It only takes one, but you can have a few. They would still be alive. They would still be alive. So what you have right now is basically an illustration of natural selection and how it works, right? They would still live. So all of these people, they're all dead, right? So, draw in the gore if you want, right? All of those people are wiped out. Who remains? Them. And if the trait was baked into their DNA, because there's traits that aren't, in your DNA. If you go work out and you acquire muscles, I'm sorry to tell you, you can't pass that on to your kids. But there are traits that are in your DNA, and your height is probably one of them. And so they would reproduce, and their offspring would be how tall? Under or over 5 foot, their children. Luckily, there's 2, because you need 2 to have kids, right? So, yeah, they'd be under. They'd be passing on that trait, right? And all of a sudden now we'd have another population. Notice now it's also vulnerable, if another UFO comes, and just starts burning all the ground, whatever, there's still something they're vulnerable about, but that's how evolution works. But in order for that to work, in order for the green species here to survive, you had to have tall and short green individuals. You can't have the green species will not go on if everyone is the same. The variability is what's going to make us more resistant to various environmental threats. Same for bacteria, same for humans, and same for stick figures, right? So the question is, how does this come about? How does this variability between individuals come about, right? And we just saw, we have a firmer understanding, a more firm understanding than we did before. We know that it has to do with the copying of DNA. And there's errors in the transcription. Kind of like if I ask you to transcribe a book, I'm almost certain that even if it's a simple task, you'd have some typos in there, right? Well, there's typos. Nature does typos. What did Darwin think about this? Well, he doesn't say much about it, partly because he's before the modern synthesis. So he didn't know about genes, and he couldn't have access to the video that we just saw. That's actually a fuller story than he ever could have dreamt of. But for instance, in this book, The Variation of Animals and Plants Under Domestication, right? So if you go dig a little bit, and here's a page 242. This is a volume 2. Let's go see what Darwin says about variability, which is his word for mutation. Variability of every kind is directly or indirectly caused by changed conditions of life. Or to put the case under another point of view, if it were possible to expose all the individuals of a species during many generations to absolutely uniform conditions of life, there would be no variability. So this is as close as you get, and trust me, to me, it would be the smoking gun. I'm still digging through the corpus of Darwin to find a clearer statement, but this is the clearest statement I can get. Was he a determinist or indeterminist? That is, did he believe it was random or non-random how these changes and mutations came about? And he was siding basically with the clockwork view. And the clockwork view, remember, says that if you can have things that appear random, but they only appear random because you don't have a full story of the universe, right? So likewise, the consensus among biologists today, right? If you ask them, what do you think about evolution? They say, yeah, evolution's right. Evolution's on the right track. And one of the fundamental forces of evolution, as we've just seen, right, there are 4, but one of the fundamental forces is random genetic mutation. I can skip the genetic here, right? Random mutation. Now, most biologists, if you sit them down and you ask them, so you believe that the universe has random parts in it? They go, no, I don't believe that. When I mean random, I mean as if random. It looks random to us because we don't have all of the knowledge. But really what's happening at that tiny microscopic scale when the DNA is being replicated, right, and those typos are introduced, surely there's some sort of purely, physical deterministic story for why it was that mistake as opposed to another mistake, right? It's not really random. So that's why you won't really see the idea of random genetic mutation, or at any rate, when you see it done, when you see that word or that concept used, it's not used really seriously because no one actually commits to the idea that there are pockets of the universe that would be random, and that would explain why we have the mutations that explain why life is so resilient, right? Why we can't wipe out the COVID virus and why there's still life on Earth despite asteroids dropping on us, wiping out, let's say, life, most of it with the dinosaurs. Still, these other little freaks, that had fur and were warm-blooded, all of a sudden they survive, right? They're like the short little green stick men, right? They survive. So they don't really believe in randomness. Peirce is going to believe in it. And Peirce is going to, in that sense, deviate from the orthodox view. Here's a quote from Einstein, right? I have said so many times, God doesn't play dice with the world. And this is not actually a quote. I don't want to be the scholar in the room here, but just if you go back to the original sources, that's not exactly what he said. But in general, he did say something about God not playing dice with the world. God doesn't take chances. And he was convinced that the universe was the clockwork universe that you just saw, just governed according to different rules. And Newton thought his main rule was F equals ma, so force equals mass times acceleration. What's Einstein's big formula? What's the big formula that Einstein is known for? Yeah, everyone knows that, right? Kids know that. It's on coffee mugs. It's on bumper stickers, right? E equals mc squared, right? This is the thing that Einstein is known for. So this is the theory of everything according to Einstein, right? Ultimately, this formula explains how all of the bodies in the universe move and interact with each other according to law. And if you keep, distilling and understanding physical phenomena, he comes up with this. And this is better, physicists tell us, than F equals ma, because it accounts for certain, phenomena like the movement of celestial bodies and the bending of light and things along those nature. Yeah, and in astronomy, Einstein's a genius in so many ways. And Einstein is a genius, so let's be clear about this, right? But Einstein was a genius in what fields? He's a genius in fields like fundamental physics, right? And physics influences a lot of what, the work that astronomers do, so there's a lot of results there. But he wasn't a philosopher, right? And one of the weird things that happens when you have a theory like this is, well, you just have to accept, right, that E equals mc squared is basically just there. It's just there. It's part of it. It has to be like, okay, why E equals mc squared? It could have been a bunch of other things. Think about it, right? Why is it that energy is equal to mass times, the speed of light squared? It's like, why? You just have to take that as a given. It's just basically there. It explains, but is not explained, right? And I'm putting here like as if it was recorded on some tablet at creation, if you will, right? It's just one of those things that you just have to take as a given. And he's fine with that, and most physicists are fine with that. But when we're going to be doing cosmology, we're not necessarily going to be happy with stopping there. We might want to say, wait a second, why this? Like, and that's a curious thing if you think about it. Like, why this? Could have been something else, right? Why not something else? Like, that's the sort of question that someone who's doing philosophy would ask, right? And if you think about it, physics, the full story involves a bunch of other different relations and laws, right? So here's a list of different laws that you learn in school when you study physics, right? There's quite a few, and all of these are quite specific, right? And it fits perfectly on my coffee mug. This wouldn't fit on your coffee mug, Owen, right? This is a little much, unless you're from a Big Bang Theory. They might put that on their coffee mug, right? Because they'd be like, hey, they tell you some complicated reason for why you need these other laws. And here are basic physical laws, right? And they govern the motion of bodies. And that's terrific and that's wonderful so far as it goes. But once again, now you have to think, well, okay, so my story of the universe, as explained by physics, which is supposed to range over everything because it explains the movement of matter, right? So bodies and matter and the fundamental forces governing them. You just have to take it as a given that these are just kind of written into the fabric of reality just because, right? All of those are there. And you might ask, well, why not something else? I mean, for each one of these, it could have been something else. You could easily imagine a different configuration of relations among the forces and whatnot, right? So why not something else? And so what we're going to be doing now is going to be asking that question. Can we dig deeper than this? Can we go below E equals mc squared, right? Can we say, why E equals mc squared? Like, can we ask why of that as well? Because remember, I told you, we philosophers, we ask why of everything. Can we just take that and can we ask why? And yes, we can. And Peirce is going to provide an answer for that. He's going to say that ultimately the universe has an even more fundamental story. There's a basement beneath the basement. If you dig beneath E equals mc squared, you have to account for why it's that law and not another. And the reason for that is the universe is governed by chance and habit taking. And that is what accounts for the physical laws that we observe. Chance and habit taking are the fundamental cosmological forces that give rise to the physical laws that we observe. And that kind of undertaking, that's not physics. That's cosmology. And it's importantly different. And I'm going to show you a video now by a fellow by the name of Lee Smolin. And Lee Smolin is a cosmologist. He's a quantum physicist, a cosmologist, and a really good one. I would recommend reading his stuff, although some of this stuff can get really hard. And he's influenced by Peirce. He finds in Peirce a lot of ideas that answer questions that he has. So very, very curious quantum physicist and cosmologist, Lee Smolin. Can everyone see him on the screen right now? And if you have more time, you might look him up on he's got videos on YouTube of conferences and stuff. I'm just going to show you a little clip. Don't look him up on YouTube now, right? Stay in this class because that's much cooler than anything you'll find on YouTube. But let's hear him talk about the difference between cosmology and fundamental physics.
My name is Lee Smolin, and I'm a theoretical physicist. I work at Toronto Institute for Theoretical Physics in Ontario, Canada. And I work on the most fundamental problems about nature. What is time? What is space? What is the universe as a whole? Where did the universe come from? What started it? What was before the Big Bang? In physics, we study systems. We study the air in this room. We study the elementary particles created by a collision at the Large Hadron Collider. We study the solar system, or the galaxy as a system of stars. And these are all parts of the universe as a whole. And it's very important that we treat them as parts of a larger universe, so that, for example, where they are or how much energy they have is defined relative to the rest of the universe that's outside the system. So the very way we describe parts of the universe as related to the rest of the universe is characteristic of the method by which we describe nature in physics. And when we raise our ambition and we come to the question of the universe as a whole, or a question that is about the whole story of the whole universe, like the Big Bang, or how the universe started, or what was before the Big Bang, we're dealing for the first time with the question of how to describe and make a theory of the universe as a whole. And this is a very different kind of theory, a very different kind of questions than the questions we're used to dealing with. And therefore it's important to stop and meditate for a while on what it means to make a theory of the universe or any system as a whole. When we describe a star, we do reference it and describe it with respect to things outside of it. We describe its position relative to the position of an observer who's outside the star. When we describe its motion, we're describing its motion relative to something outside of it. and so on. And that works. That's a legitimate way to do science, except for when we come to the case of the universe as a whole. And then we have to describe a system that contains everything. There is nothing outside the universe. And there therefore is nothing to describe the universe with reference to. And this means we need a very different kind of structure, a very different kind of method, a different kind of theory when we come to study the universe as a whole. Because there's a tradition of thinking deeply, seriously, and critically that goes back centuries, which is what you learn when you study philosophy. Now, if you're not interested in a fundamental question, like the nature of time, or what is matter, or the nature of the universe as a whole, but you just want to apply known laws to known phenomenon to understand them better, to understand the behavior of a solid or of a gas, or a star, or something isolated like that, you can proceed without much knowledge of philosophy. You can proceed pragmatically, we like to say. But if you want to ask the really deep questions, there are these traditions of human beings grappling with the same questions. They go back hundreds of years. And not only is it good to know them because it gives you a storehouse of ideas, it allows you to understand your own thinking, because what you discover is that unless you're extraordinarily special and unusual, your thinking is shaped by the philosophical legacy that underlies our civilization.
So there you have it. You want to be a good physicist, you can just do physics. But if you want to be a good cosmologist, you want to study the universe as a whole. He kept using that expression. That's what cosmology is. It's the study of the universe as a whole. He says you have to study philosophy, and you're going to have to resort to other kinds of explanations and other kinds of laws, because essentially the question we want to ask right now is, okay, fine. Let's say that the Einsteinian story is correct, right? And E equals mc squared. Why that law? How do laws come about, right? What is the law of laws, essentially? And Lee Smolin, who you've just seen, reads some Peirce, and he's been influenced. I mean, he works on his own, but he's one of these people. And the smarter you go up in the hierarchy of intelligence, the higher Peirce is regarded, because people who can understand what Peirce is saying realize the man was not crazy. That's what we're going to do today. We're going to bake some laws together. So is everyone ready? We're going to create a universe. It's going to be our first of two universes we're going to create together. If you're ready, tell me ready. We're going to create the laws of physics together. Let's create some laws of physics. I'm going to share with you Charlie Peirce's recipe for creating laws of physics in a laboratory, right? Let's create some laws of physics. Let's imagine this situation, right? Here's a rock, and here's a hand holding a rock. You all know in this world and the way things are based on your experiences, what happens if the hand releases the rock? It falls, right? And you represent this fact, and you can forecast and predict what's going to happen in virtue of a habit you have. You form the habit based on experience, right? And you know that your habit matches the regularity in the world. Your habit of, predicting these things, right? That, released rocks tend to fall, right? This maps onto the world, and you're like pretty confident that this is not going to be wrong, and you go ahead and you predict that. But that's based on, you have had multiple instances, as humans have seen multiple instances of rocks falling. I want you to now imagine that this is the first time a rock will be released, right, from a hand ever in the history of the universe, right? Now, there's two possibilities. If we ask, this is the first time a rock is ever going to be released, or any object is going to be released from a hand on a planet, I'm going to keep spelling that out, right? What will happen? Well, there's two ways of looking at this, right? If you think this, let's go back. If you think this, that somehow, baked into the universe was right, the laws of physics, then the very first time this was falling, the very first time this was going to be released, what would happen? So E equals mc squared has been baked into the universe. The first time the rock's about to be released, what's going to happen to the rock? The universe has been set. It's going to fall. Yeah, it's going to fall. It's going to go this way, right? Why? Because, you know, F equals ma and E equals mc squared, right? That's gravity, exactly. That's been baked into the universe, right? But that requires you to take as a given, right, that it's been baked in. You have to accept that as a given. What if you're not happy with that? What if you think that's not primitive enough? Like, that renders one fact explainable, but by appealing to another fact that you're now making unexplainable, which is why those laws? Like, seriously, like, why those? Right? Like, interestingly enough, and you can think why the fine-tuning argument for the existence of God, for instance, is so popular. Like, why those? Right? It's like, it could have been something else. Well, let's not make that assumption. Let's go a different route. Let's go the Peircean route. This has never happened before. This is the first rock ever to be released, right? According to Peirce, if it's never happened before, and it's the beginning of the universe, this is completely up for grabs. There is no law that's already set in motion. The fundamental ingredients of the universe aren't going to be laws, but chance and habit taking. These are the only two ingredients that we're going to use. It's like flour and water. You can make flatbread, right? You can make so much with just flour and water. We're going to build a universe out of chance and habit taking, right? And so what we're going to do is we're going to build the laws of the universe based on that. Now, if this has never happened before, according to Peirce, it could fall, it could go up, it could go sideways, it could go this way. Anything could happen. It could stay still, right? Anything can happen. Pure spontaneity, pure chance, right? And John writes, would habit taking apply here if it is the first time ever it's happened? No, habit requires more than one instance, right? It's just like you can't have a habit. If you do a hole in one, but it's the first time you ever hit, you know, it's pure luck, right? You've never hit a ball before. I can't credit you with being a good golfer. It's absolute pure luck, right? There's complete chance right now. John, can you see that? You need more than one instance. Yeah. So right now it's completely spontaneous, right? I'm going to basically limit, just for the sake of our little micro universe, I'm going to limit it to 4 possibilities because we agreed there's a zillion possibilities, right? All sorts of things could happen. It could also vanish out of thin air. It could go poof in a puff of smoke. It could switch into green cheese, blue cheese. You know, who knows what's going to happen when that hand's been released? We're at the beginning of the universe. We're a second into the universe. This has never happened before. It's completely unprecedented. The universe itself doesn't know what's going to happen because there's nothing written on a tablet anywhere, right? The only fundamental law that's going to govern our micro universe is going to be the following. This is the one law of laws. It's the law that's going to explain all other laws. Repeat randomly from all that has happened before. All right? That's going to be the one law. Now, what's happened before? Has this ever happened before? Based on what I've just told you. Has this ever happened before? Someone's about to release a rock. Has this ever happened before? No. So we can't repeat randomly from what's happened before. In this case, it's just going to mean anything can happen. Because this has never happened before. There's no precedent. It's like a judge. You know, when I teach philosophy of law, the cases that are the most interesting are when a judge is in front of a case for which the judge, she can't turn around and say, hey, what did you folks think? There's no one to turn around to consult. There's no precedent. There's no legal precedent. There's no legal precedent right now. There's no metaphysical precedent. So we're going to make it such that there's only, let's give ourselves 4 options, right? Because tracking all the different possibilities would be too hard. I'm going to give myself down, up, down, left, right. I'm like a crosshair for a video game, right? Up, down, left, right. So let's say we're going to call this 1. We're going to call this 2. We're going to call this 3, and we're going to call this 4. So let's just reduce this to 4 possibilities. And right now, right, if we were to consult the one law of laws, repeat randomly from what all that's happened before, really anything can happen, quite literally. Like anything can happen. It could go up, it could go down, it could go left, it could go right, right? So that's the first state of our universe. So state number 1, right? So we're baking the laws of physics. We're going to use Peirce's method to develop a universe, right? So we're going to say anything can happen. That's going to be the first initial state. That's the first initial state of our microcosmos, our model of the universe. Anything can happen, and that's where we are at the beginning. So in the beginning, what in the beginning? In the beginning, anything can bloody happen. It's not written in the stones. It's not written in the tablets. You know, like what, before the Big Bang, E equals MC squared was settled? It's like, no, none of that is settled. Anything can happen, all right? So far, so good. If you're following along, say good. So far, so good. First state of our story here, anything can happen. Who the hell knows? Cool. All right. And remember, the basic ingredients are chance and habit taking. And really, we're going to run our whole universe, right, on chance. And habit taking is basically the law, the one law of laws, right? So I'm going to actually resort to chance here to figure this out. I'm going to use a little tool here, right? So let's have a look. Hopefully this will screen share well. Can everyone see a wheel here? I'm going to spin the wheel. Can everyone see that? All right, so I'm on a random number generator here. I've given myself 4 options, 1, 2, 3, 4. Those stand for up, down, left, right, and whichever way I've just assigned it, right? I'm going to spin the wheel. All right, so here I go. Actually, can I have a volunteer? Someone give me a volunteer. I want someone else to spin the wheel. It'll be more fun. Who wants to volunteer to spin the wheel? John volunteers. John, please press on your screen where it says spin. Say yes when you've pressed it. There you go. Oh, John's pressed it. Thank you, John. I'm just kidding here. John can't really press his screen. All right, and the verdict is 4. And everyone can see here. I want to be ultra transparent about the fact that I'm really using chance here, right? At any rate, 4. So where did the rock go here? According to the wheel that said it was 4, where did our rock go? So, sorry, I just erased it. It went to the left, right? So, yeah, it went to the left. All right, so that's where it went. It went to the left, right? So the first state was completely unprecedented. And now we've just resorted to chance. And it turns out when you release this rock on this first occasion, right, it went to the left. So we're going to go over here. And now we're going to type in that it went to the left. We're going to record that for posterity. We're going to say at the beginning, anything could happen. And so when it was first released, what happened? It went to the left. So I'm going to say left now. All right. So now we're at time t3. At the beginning, anything could happen. After one drop, it went to the left. Now, our law says, the law of laws, repeat randomly from all that's happened before. But what's happened before? 2 things have happened before. First, anything could have happened. That was the first thing. And second, it went to the left. Now we're about to do this. So this is now our third occasion to do something. All right, so so the third state, we're going to drop the rock again, right? And now we're going to resort to our law to figure out what to do, right? What's going to happen. It says repeat randomly for all that's happened before. Well, 2 things have happened before. Yeah, there's no guessing here, just taking chances. Exactly, Ariana. I'm literally using the wheel. I'm not asking you. I'm not guessing, right? Oops, I've erased what I said. All right, so I got to be careful here. So anything can happen, right? That's our first thing. Anything can happen. All right, cool. And then the second one was left, right? And now we have how many options to choose from? So now what we have is we have 2 options to choose from in determining what's going to happen at 3, right? So I'm going to go back to my wheel picker to figure out which of these 2 options, 2 or 1, is going to happen. Because our rule says in order to figure out what happens, right, consult the past and pick randomly. Probably my arrow should go this way. To figure out what happens at 3, go back in the past and pick randomly from what happened before. And we have 2 options here, right? So what I'm going to do now is I'm going to go back to my wheel. So here I go, right? I'm going to reduce this to 2 options. So now there's 2 options. There's option number 1, which was anything can happen, and option number 2, which is go to the left. All right, who wants to spin the wheel? Andrew spins the wheel. Go for it. cool. So now we go back to 1, right? So 1 was anything can happen. So what does that mean? So anything can happen. Now it's going to be a surprise, right? Anything can happen, my friends. So anything can happen. It can go, and we've limited ourselves to 4 directions, right? It can go this way, or this way, or this way. I'm going to go, let's assign these letters. 1, 2, 3, 4. I declare a rock war. All right, so 1, 2, 3, 4. Anything can happen, folks. Anything. I feel like at a carnival of some sort, right? Anything can happen, people. All right, so here we go. We're going to use chance once again. I'm only resorting to chance here. I'm only resorting to chance. Who wants to spin the wheel to figure out what's going to happen to that rock? Which way is it going to go? Anything can happen. Spin the wheel. Who wants to spin the wheel? Arjun is spinning the wheel. Here we go. Two. All right, cool. 2. So let's figure out what that means. 2 means it goes right. So these other options not happening, right? It turns out it went right. So that's what anything can happen. The thing went right. Cool. So let's go back in time here. And we're going to write what? We're going to write at 3. We're going to write right. Cool. Right. All right. What's going to happen at time T4? What's going to happen at 4? Well, what does our law say? Our law of laws says repeat randomly from all that's happened before. So now we have to figure out what's happened before. What's happened before is that anything could happen. It was pure randomness. Once it went left, once it went right, and those are our 3 options. Those are the 3 options to choose from. So we're going to once again just rely on chance to figure out what's going to happen at the 4th moment. All right? So let's figure out what's going to happen at the 4th moment. Let me screen share that with you. And now we're going to need 3 options, right? Here we are. We got 3 options. Who wants to spin the wheel? Ariana, allez-y. 1. Good toss, good toss, good spin. All right, so now that means what? Based on what I had said, well, actually, I didn't assign. Well, actually, I did. We were here. That's right. So 1 means anything can happen. So anything can happen. So I'm gonna skip the wheel. Ariana, you just get to make stuff up. Ariana, which way do you want this rock to go? Up, down, left, right. Just skip us a step. Up. Cool. Ariana says up. Ariana, can you do me a favor? Just to speed up the process for pedagogical reasons, because Papa Bear's looking at the clock. Could you say right? All right, cool. Just because we could do this, but I'm just looking at the clock. I think you folks are starting to understand how this is going to work, right? Let's say it went right, right? Because anything could happen, and it went right. Cool. Let's find out what's going to happen at time number 5. How do we do that? We refer ourselves to what's happened before, and we pick randomly from what's happened before. What's happened before is right, left, and anything can happen. What do you think is the likeliest chance? What's the likeliest outcome of this, by the way? So what's the likeliest thing to happen at 5 if you had to bet? You got 4 options. Right would be the likeliest thing. Let's figure it out. Let's go back to our wheel now. Let's go back to our wheel. And now we have to pick between 4 things, right? Who wants to spin the wheel? We're baking a universe. We're baking laws out of pure chance. Who wants to spin the wheel? Reese is going to spin the wheel. Here we go, Reese. 4. Well done. So 4 means what? So 4 means, so we were figuring out like which of these past events. It turns out it's 4. So the rock is going to go which way when we drop it? It's going to go right. It's going to go right. All right, let's do it again for 6, right? How do we figure out 6? Which law is going to govern this rock? What's going to happen to this rock? Who the hell knows, right? Well, we say, well, repeat randomly from what's ever happened before. And it's, who the hell knows right now? But if you had to bet right now at this stage, and we're at stage 6, if you had to bet Where's this rock going to go now once we release it? Get to bet. Probably right, huh? Because look at our options. We have to consult what happened before and pick from that. We have 5 options to choose from. 1, 2, 3, 4, 5, right? And those options are right, 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 left, and anything can happen. The wild card that was at the beginning, right? So what's going to happen at 6? So let's screen share this. Let's spin the wheel. I need a volunteer for my wheel. Who's my volunteer? And we have 5 options. Volunteers, please. Owen gives it a spin. 5. Well done, my friend. And so what does that mean? Well, it now means that, let me just undo all this without erasing everything. It means that the rock is going to go which way? Going to fall which way? It's going to go right. It's going to go right. And once again, what will we do for 7, right? And now, what will we do? We would consult what would happen in the past, right? And repeat randomly from all that's happened before. So let's pause here, right? What do you think is going to happen if we spin the wheel with 7 segments, right? And 6 segments, and 4 of those 6 represent right. So 4 of the 6 possibilities, right, represent right. It becomes more lopsided towards the dominant option. That's right. It's more likely right, right? And it's going to probably go that way. And let's try it. Let's try it. I'm going to spin the wheel. This is going to be my last spin of the wheel. We have how many options to choose from here? 6. So let me set this up. I'm going to spin the wheel. Where will this rock go? Again, notice how the rock could go anywhere. In the strict sense of the rock could go anywhere, right? But our universe is starting to fit into a bit of a pattern here, right? And Ariana's, that's what's happening. It's emerging, right? How many options did I have? Did I say I had 6? Or let's spin the wheel. I'm going to spin the wheel this time. 2. Beautiful, right? 2. So what's going to happen at 7 now? If I've landed on 2, where's the rock going to go? It's going to go left. That's right. So there's still room for surprises. There's still room for surprises, right? And there's always going to be room for surprises because at the end of the day, there's still the anything goes. But what's the dominant option still? If I'm going to spin for 8, what will be the likeliest one? Still right, right? And every time right wins, every time that one possibility wins, it's more and more likely as time goes by. It's more and becomes more and more likely. Each one of these steps. So let me just pause now. Let's just do some philosophical morals from all this. The only ingredient that we use so far is chance. Chance both in the initial state, chance in picking out which of the different states we pick from, right? Yet, because of this one rule, this one law of laws, right? Habit taking starts to emerge. The universe starts to have a bit of a habit right now. It's a bit soft. It's a little hard. It's hardening as we go. Right now, it looks like who's going to be the winner in this universe? Where will rocks go when they fall? It looks like very early in the game to say. It's too early to call the hockey match. But this universe is slowly growing and developing. Where will rocks fall when released in this universe, it seems? Probably to the right. And we'd have to keep testing. Maybe I'm wrong, right? Maybe I'm wrong. But when you release a rock, it'll go to the right. And of course, if you come in really late in the game, all right, so let's go really late in the game here, right? Let's imagine, right? This is because we're 8 milliseconds into the universe, right? How many times have things been released? How many times have rocks been released since the beginning of the universe? How many times have objects been released since in your universe, in the universe we know and love, Reese? In this universe that we know and love right now. Like an almost infinite, a finite but unfathomable number right? Let's say a googolplex, right, which is an insanely high number, right? A googolplex. So let's say a really, really high number, but GP doesn't convey it enough. Let's just say like let's just make 1,000 still a big number, right? Of course, if you live in this universe and you were born at time t1000, chances are all the rocks you saw falling went where? Let's say it starts to, let's say this keeps working itself out, right? Right has a great advantage, right? Let's say it ends up becoming right, right? If you live in this universe and it's 1,000 times now, this has happened 1,000 times, in that universe, when you see a rock falling, it's always gone right ways. And you're going to say, well, there's this law of gravity. And the law of gravity is that when you release an object, it goes right. And of course, now you're going to think, you know, go right is on the tablets. You're basically going to say, oh, look, you see, go right. That's one of the rules, right? When things are released, they go right. It's one of the rules. But it wasn't one of the rules. It just happened by chance. Everything happened by chance. It's just that the chance eventually started to settle into a regularity, and the regularity got confirmed because it got confirmed, which gave it a greater chance of being confirmed, and then the regularity became more regular, and all of that was built on one ingredient alone, namely chance. And in our world, things go down. But Peirce is going to say they could have been otherwise. Things, when you drop them, could have done all sorts of things. But we're coming in really late in the game, and the world that we're observing, right? The world that we're observing is the world over here, very late in the game, ... A lot of things has happened, but in the beginning, there was chance. Pure, unadulterated chance. And Peirce is going to say that's much better than to say in the beginning, there was E equals MC squared or something like that. The laws weren't set. The laws were not set at all. They were not set. They became set with time. All that we had at the beginning of the universe in the primordial soup of the cosmos was chance and this one law of laws. My friends, does that make sense? Is that clear? Tell me if that's clear. If it's clear, write clear. If you have a question, write your question. And notice here, we cheated a little bit. We asked, you know, because I wanted to start seeing a direction in the habit taking. I asked Ariana to say, oh, please just go there. But if you ran this experiment, and you can do this yourself, right? Try it yourself. Don't take Peirce's word for it. Just with chance, eventually, if you're governed with that one principle, repeat randomly from all that's happened before, you start with pure spontaneity. All sorts of things might happen. One of those things among the others tends to happen, and then that starts to give a predilection to that thing. More things are likely to happen as a result of the one happening. And once it has a predominant advantage over the others, maybe once in a while other options won out, but once there's a predominant advantage, right, that predominant advantage makes it look like it's now a law, right? But notice what happens. Chance was at the beginning, and even now, in our world, when we drop, according to this account, when we drop a rock and it goes down, is there a possibility it may do otherwise, according to this account? When you right now drop a rock, might it surprise you and just go, yeah, it might. It might, right? Why? You're right. Owen, Reese, Andrew, you're right. Why? It might surprise you. You drop a rock and it might go this way. Anything can happen is always an option. Yeah, because of chance. That's right. Look here. This first thing was chance. This first primordial thing here at the very beginning where we started, that initial state was anything can happen, right? Anything can happen. We never actually leave that, right? That's always one of the possibilities. Now, of course, when we spin the wheel now, right, what is it like? Well, when we spin the wheel, that's like me saying, let's go back to the number picker. When you let a rock drop now, it's like this. So what's the maximum? 1,000. All right, how's this? Let me share screen that with you. If it falls on 1, the number will do something wacko. Anything else, it'll fall down. And we spin the wheel. Let me just spin the wheel. what do you think is going to happen? Will it be another number other than 1, or will it be 1? And you're like, hey, it's any other number than 1. 1 would have been the one where it surprises you. It does something wild. Or an earlier number in the universe, let's say, maybe it went left at, what did we say? It went left on the second run. So let's say 2 is going to go left. The earlier numbers, 1, 2, 3, 4. 1 is like pure chance. 2, 3, 4, 5, 6. You go left, right, up, down, left. And then it's like, at some point, it started settling to down, 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 right? And of course, if I spin the wheel again, what's the safest prediction? Where's the rock going to go? Safest prediction would be up, down, left, or right. Where would it go? The safest prediction. Down, of course. Let's test it again. And after several spins of the wheel, you're like, I got this figured out. I figured out the law. Things that are dropped go down. I've got my law of gravity. But the law, now you have a choice. How do you gloss it? And Peirce says you don't have to think that it was baked into the universe just because why would it go down? It's not obvious. Could have gone different ways. You don't have to bake it into the universe. All you can do is you can say there's chance. It could have gone all sorts of ways, but then the universe took on a habit. I took on a habit as well. My habit maps onto the habit of the universe, but just as my habit can always err, my habits can always break down, there's always room for surprise in the universe, right? And that's the element of firstness and surprise. And when you get the surprise, you get the firstness is the potentiality. The surprise is the secondness. You could be shocked, right? But there's one rule that explains all the rules. All the laws of physics are explained by this one principle, this principle of habit taking coupled with chance, right? Do you like that account? What do you think is more parsimonious, right? So it was written in the tablets, or it just kind of settled into place? What do you think, my friends? Because that's our first micro-universe. It's that, or it was written in the tablets. It's like, then the laws themselves become answerable to another more fundamental law. Yeah, this really mind-bending stuff, really mind-bending. And a big departure from the way we think about things, because precisely it's trying to go deeper. It's trying to do cosmology in a sense that Lee Smolin spoke about a moment ago. Yeah, the Peirce is so bloody weird. It's just so wild. We're going to read from his words, literally what he says about this, right? So that's our first micro-universe, right? And we saw it together. We ran the experiment. And only with chance, and you will get a pattern emerging. And the pattern emerging will eventually settle into place. And after having settled into place, and remember his work on geodesy, also the swinging of the pendulums, and how the little micro variations kind of even out. I think a lot of that influences all of his philosophical outlook. And so we can use also chance and habit taking now to explain other things. Let's make some creatures. Is everyone ready? We're going to do another toy universe. Another universe in your kitchen. Creating a cosmos in a petri dish. Is everyone ready? Ariana's ready, because I need you to be open-minded and to play with me on this, because it's going to be another wild and wacky ride. And then we'll do the Peirce packet together. But this one's going to be another mind bender. All right. So let's imagine now. We're going to make our micro-universe. Our micro-universe is going to be really simplified. It'll be different from what we just did, right? Let's imagine a micro-universe that's just a grid like this, right? So this is going to be a stupid grid like this. And on our grid, there can be certain of these little cells here. Can everyone see my little red dot? Can you see my little red dot on the screen right now? Cool. Let me zoom in a bit. Drag this over here and zoom in, right? Some of these little squares, right, can be filled, and some can be empty. So, for instance, this is filled, this is empty. I'm going to put just a little dot here just to signify that they're filled. That's all our universe is going to be comprised of: a grid with empty squares and filled squares. That is it, all right? And they're going to be governed by law. So let's imagine now that we're at the, I don't know, billionth or trillionth or billionth of a trillionth, iteration of our universe. And the laws of the universe have settled into place. And in this micro little universe, anything could have happened at the beginning, but it's settled into 4 fundamental laws. In this universe, these are the 4 laws that govern the appearance of little filled cells. For a space that's populated, so if you're like this, for instance, right, and you're looking at a cell over here that's populated, so where my little red dot here, right here, each cell with one or no neighbor dies as if by solitude. So you can see for each cell over here, for each square, there's, oops, that's too big. For each square, there's 8 neighbors, right? So like 1, 2, 3, 4, 5, 6, 7, 8 neighbors around any given square, right? Now, for one square over here, it has 1 neighbor, right? If it has 1 neighbor or no neighbor, what's going to happen the next moment? It's going to disappear, right? So it's no longer going to be there. So here there was something, right? And the next state there was going to be nothing. Here, right, where I've got my little cursor, how many neighbors does this little one have? 2 neighbors, right? The other law is that each cell with 2 or 3 neighbors is going to survive the next moment. So in the next moment, it's going to survive. It'll still be around. So this one that over here is going to survive in the next moment, right? And so it'll be that's one of the laws, 2 or 3. Here, how many neighbors do I have? Where I've got my cursor right now. 5. 1, 2, 3, 4, 5. All right. If a cell has 4 or more neighbors, it's going to die in the next moment as if by overpopulation. So in the next moment, it won't be there, right? Notice how this cell came to life here, right? That's because of the final law, which says that each cell with 3 neighbors becomes populated. So if you have a space that has nothing in it, so right here, you can see there's nothing in it, but I've got 1, 2, 3 neighbors, it's going to come alive in the next moment. However, notice how its neighbors are going to die. Why are they dying? Why are the neighbors dying? In virtue of which of these 4 laws? Why are the neighbors that were there that gave it life, why are they dying? In virtue of which law? Yeah, the law number 1, that each cell with 1 or 2 neighbor dies. So the laws are applicable everywhere. The 4th law over here, right, is going to make this one come alive, but in virtue of this first law over here, right, the other neighbors that gave it life, they're going to die. And that's all our universe is going to be. That's all it's going to be. All right. Is that clear, everyone? Just there's 4 laws, a grid, little squares, little squares either come into being or not at any given moment in virtue of these rules. That's all it is. That's our micro universe, right? If that's not clear, I know you can't see where this is going to go yet, but if that's not clear, tell me and we'll just clarify it. And as always, in order to learn, you must desire to learn, right? So, yeah. So you have to go with me on this at the beginning. Cool, clear-ish. Well, let's see it in practice. There's no better way to see this than to see it in practice. So here we are. Can everyone see a gray grid? Can everyone see that? A gray grid of squares? Cool. So we're gonna work in this little micro universe of ours, right? I'm gonna take my my little cursor here. I've got tools on the bottom here. One of the tools is time, another tool is zoom. Notice I can zoom out. Right now I'm zooming out. You can see the grid space has gotten really small. This grid extends in all directions. I can also scroll. I can take my hand. Right now I'm scrolling, and I can zoom in. So I'm going to zoom right back in. And if I click with my mouse, I make a little square and I fill it up. I fill it up. Now, the next moment, what's going to happen to this one little grid that I have filled up? The next moment, what do you think is going to happen? It will die. Indeed, it will. In virtue of what? Peirce. Law number 1, it's got, you know, not enough little neighbors around it. So in virtue of the first law, it's going to die. Let's do that. I'm at the slowest possible time, right? There you go. It just died. I can click the timer and then look, you know, the time goes by. You can see the numbers at the bottom, right? Over here. There's the numbers going by, state 9, 10, 11, 12. Our universe is unfolding. This little thing died, never to return again. All right, well, there you go. Let's reset everything. Let's imagine I have this. What's going to happen to both of these little squares the next moment? Are they going to live or die? They're going to die because once again, there's not enough. So let me press start. Boof, they're gone. Right? All right. Let's see this situation here. What's going to happen where I'm at right now? I'm kind of flickering it. What's going to happen at this space in the next moment? It'll come alive. It's not just going to survive because it's not there. It'll come alive. Like right now, there's nothing. One will appear because there's exactly 3 around it. Right? If there's exactly 3 things around, at the next state, it'll appear. But then after it appears, what's going to happen? So once it appears, what will happen to those 3 over here? They will die, and it will die too. So let's play that out. Poof. Let's do that again in slow motion. Let's reset that. I'm going to play it. Poof. I'm going to play it. Poof. Cool. It's dead. I know, it's so sad, right? What about this? What's going to happen to the block in the center in the next moment? The block that's in the middle of the 3. What's going to happen in the next moment? It will stay. What about the ones at the tip? Left and right tip. They will die. And what's going to happen here and here? So here and here, what's going to happen in the next moment? They will come alive because they have exactly 3. That's right. They will come alive. So let's play this out. I'm just playing right now. It's playing. At each state, notice when it's vertical, same situation repeats itself. The middle one survives. The tips die. But then these, right, come alive because there's exactly 3. So let me play again. Cool. Let me pause. So far, so good. Can everyone see how this is working out, the consequences of these 4 laws? If it's so far, so good, tell me up. Tell me yes. Tell me something. I just want you to get the rudimentaries of this small little universe. The physics of it are really easy, right? Of course, notice how, according to the story I told you before, we don't have these rules for free. They emerged out of chance, right? But here we are. All right. Let me have some fun now. Let me clear this. I want to do this structure here. What do you think is going to happen? Well, once again, you can go ahead and calculate this. The computer can do it for you. Like, for instance, this one over here, is it going to live or is it going to die? I mean, it's got only 2 neighbors. This one cell over here, is it going to live or die? It's only got 2 neighbors. Like, if you look at this cell, it's got this neighbor here and this neighbor here. It's only got the one at the tip here, at the upper right tip, it will die at the next moment. Right? The upper right tip, it will die because it only has 2 neighbors. Can you see that, everyone? I can't zoom in more than that. Actually, let me see if I can. Oh, that's even better. Upper right tip. Yeah, the upper right tip will die, right? Because it only has 2 neighbors. You need 3 to survive. You need 3 to survive, I believe. Let me just go back to my rules. But yeah, unless I'm wrong about that. Yeah. No, it will survive. You're right. 2 or 3. You're right. Reese, you got it better than me. Yeah, it will live. Sorry. It will live. The bottom one here, what's going to happen to it? Bottommost one. Looks like a bit of a question mark. It will die. All right, so you know the drill, right? Let's play this. Let's zoom out a little bit, right? And let's see what's going to happen to this particular configuration. I can pause at any time, so I'm 2 states in. Can everyone see the 2 at the bottom right? If you can see that right, yes. At the bottom right, it says 2. That's the number of states that we're in, right? Let me zoom out a little bit. All right. I'm just going to press play now, and it's just going to keep on doing it for me. Tell you what, I'm going to speed this up a little bit. Speed this up a little bit. Speed this up a little bit. Let's zoom out. It's moving. It looks like a living organism. Where is it going? If you had to predict where it's going next without counting all of the little squares, north, south, east, west, northeast, northeast, where is it going next? Ah, stop. I don't know why I'm doing this. Okay, stop. Let me just replace it. Where's it going to go next? Now that my mouse is not agreeing with me. All right. Let me just do this. It's kind of cute, right? It's going to go north, northeast. Let's see if that prediction bears out. Let's see if that prediction bears out. I'm going to zoom out a little bit. Here we go. Here it goes. It goes. Whoa, it's out of sight. I have to drag and get even farther to see it, right? It's kind of cute. It is kind of cute, right? It is really kind of cute. And in fact, in this little micro universe, you can start giving them names. And this one's called a glider. It's a lovable little creature, actually really, really important little creature in this universe, right? I'm going to have some fun. I'm going to show you one that I made up, right? And it's going to have some surprising consequences. Let me see if I can remember correctly how to draw it. This is one that I made up or discovered, all right, which is an interesting distinction. I'm going to slow down the time. Look what's going to happen. Are you ready? I'm gonna play this out. I'm gonna put it at the slowest speed. All right, here we go. It's growing. It's trying to communicate. Isn't this a complete mind trip? It's symmetrical, that's right. Let me just pause, just drag this down, resume. Did any of you see this coming? Let me zoom out a bit. Let me speed this up. Reese says, does it ever find a stable pattern? You know what? You can't, there's no principled way of predicting that, Reese, unless you let it play out. For really interesting mathematical reasons, there's no way of actually predicting whether or not it'll ever achieve a stable pattern. You have to actually play it out, and then once you know, you know. Let me pause. I just want to make sure it's in the center of our screen. I'm going to speed it up just a smidge. Oh, there we go. It reached. But you know what? It's a big universe out there. Let me pause. It's a big universe out there. And somewhere out there came a glider. Did anyone see on the lower left there? I made a little glider. What the heck's going to happen? I don't know. Let's do this. Glider alert. Are you as excited as I am? I'm giddy. Like I'm so excited. If you were looking down in a petri dish, right, you'd probably think this thing was bloody alive, right? Let's have some more fun. This is where I told you this part would get really crazy, all right? So now this is going to get completely wild. Look, you can imagine if I did this, can we all agree I'm doing this randomly and by chance? Can you agree? Look, I'm just going to fill stuff up. I'm making shit up here. I'm just doing this. Can we all agree? Type agree if you agree. I'm just making this up. In fact, look, I'm just going to populate these things like whichever way, right? I could drop a bag. You know, if you ever dropped a bag of rice, the rice will just go all over the place, right? You could scatter rice all over, right? Quite easily. Like you could drop a whole bag of rice. And if you did that, let's say you purely randomly, right? And you went ahead and you did that, you could find yourself with something like this, right? This looks like can everyone see this really well? Can you see that? What does that look like to you? Looks like it's whatever, right? It's like a mishmash, right, of stuff. All right, let's see what this does. All right, so hold on to your hats, people. Let's see what is going to happen. I'm going to zoom out for this one. So just to zoom in here, just to be ultra clear, right? Look at how this looks. Like, I mean, you can imagine if there was an infinity of space and by chance, the entire space would get filled up randomly. Surely one region of this space would look like this. So let me say that argument really slowly. If we have an infinite grid that extends in all directions and you fill the entire grid randomly, surely somewhere there would be a region where this particular shape would occur. Do you agree? Type agree if you agree. Like I'm talking like an infinite amount scattered by chance. There's bound to be one of these bloody things. One of these, right? All right, cool. Let's see what's going to happen with this one. So hold on to your hats, people. All right, hold on to your hats. Here we go. Can everyone still see it? I zoomed out. Can you still see it? Type yes if you see it. All right, I'm going to get the time settings just right here, hopefully, so you can have enough of fun seeing us go. Here we go. Woo! It took me all my effort to stay silent and to wait for your responses. I'm going to speed it up a little bit. It's going around leaving a trail of turds. And it will keep going like this forever unless it meets up with something, in which case we can't tell what's going to happen. let me zoom out. Let me scroll down here. Let me pause first. When I scroll, I think it's better. All right, let me sped it up. Look at this creature. If you want to put something in its way, let's do that. Let's do that. What I'm going to put, it's called a block. I'm going to put a block in its way. I have no clue what's going to happen. My friends, you're looking at a universe in a petri dish. I told you you'd be in for a wild ride. Now, okay, so I don't know what, I'm going to speed this up because I want to know where this is going to go. Oh, look at that little glider. It's printed out a glider. The glider's going to hit a block. Oh, something's happening. Oh, another little glider. This thing generated another little glider. Let me pause this. Oh, look at these little gliders coming out. There's more gliders coming out. It made babies. The origins of life. It gave birth. Where are these gliders going to go? What are they going to hit? Right? What else is going to happen? Who the hell knows? Where's this glider going? If it's an infinite space where everything was distributed randomly, right? What's going to happen? My friends, you're looking at chance and habit taking in the flesh. You're looking at a Peircean universe that's working according to laws that have presumably come from somewhere, and we saw the origins of that in chance, right? Chance distribution, and then via habit taking, all sorts of little configurations start to arise. And if you have that, my friends, you have a story of where the universe come from, essentially, right? These things are now static. They've reached the point where they've taken on, their habit has become dogmatic, if you will, right? Like if you play them, that structure here, let me just zoom in, right? This structure over here has become kind of cold and stop evolving, right? But it only takes one little thing to trigger it back into motion. So let me just pause. I'm going to give you the link to this stuff after we're done. But everything came out of what? 4 laws. And we saw a moment ago, because that's what we did, how to bake a law, right? We figured out how to bake physical laws. Chance and this one law of laws. Repeat randomly from all that's happened before. Once these 4 laws solidify into, once the laws solidify into, let's say, these 4 laws, distribute randomly something, more chance, right? And then what you get is all sorts of stuff. This is Peirce's theory of the universe. It's his theory of everything. Is everyone ready for the Peirce packet now? Is your mind blown? It's his theory of how we came about. It's a story of everything around you that you see, living and non-living, rocks falling, little squirrels skirming about, yourself. And I could blow your mind even more, but I'm not going to do it. Stick around after class if you want. I'll tell you something about what we just saw that could blow your mind even more. All right, let's do our Peirce packet together. Now we're going to hear it from the wild man himself. Cosmology aims to develop a theory of everything, literally. This is from his entry in the 6th century dictionary. Cosmology is the general science or theory of the cosmos or material universe, of its parts, elements, and laws, the general discussion and coordination of the results of special sciences. It can also be understood as that branch of metaphysics which is concerned with the a priori discussion of the ultimate philosophical problems relating to the world as it exists in time and space. Most cosmologies dismiss chance, but chance must be instead be put at the core of a correct account. Now, metaphysics has always been imitating mathematics. Geometry suggested the idea of a demonstrative system of absolutely certain philosophical principles, and the ideas of the metaphysicians have at all times been in large part drawn from mathematics. This led to determinism. However, based on my observations as a scientist and mathematician, I contend that we can have no reason to think that every phenomenon in all its minutest detail is precisely determined by law. That there is an arbitrary element in the universe we see, namely its variety. This variety, which is crucial to Darwinian evolution, must be attributed to spontaneity in some form. Guesses are to inference what mutations are to evolution, since they're the source of originality, and some survive and others don't. The function of abductive inference or guessing is not unlike those fortuitous variations in reproduction which played so important a role in Darwin's original theory. In point of fact, according to him, every step in the long history of the development of the simplest organism into the man was first taken in that arbitrary and lawless mode. Whatever truth or error there may be in that, it is quite indubitable, as it appears to me, that every step in the development of primitive notions into modern science was in the first instance mere guesswork, or at least mere conjecture. We tend to guess correctly because we're connected to the world that we're trying to know. It is well within the bounds to reckon that there are a billion, in other words, a million hypotheses that a fantastic being might guess would account for any given phenomenon. For this phenomenon would certainly be more or less connected with in the mind of such a being with a million of other phenomenon, for he would not be restricted to contemporaneous events, and it might be supposed that the special determination of each was connected with the special determinations of each of the others in order to produce the observed phenomenon. Hence, it would be practically impossible for any being, by pure chance, to guess the cause of any phenomenon. If a human examines all the foolish theories he might imagine, he will never, short of a miracle, light upon the true one. Indeed, even with the most rational procedure, he never would do so were there not an affinity between his ideas and nature's way. A good cosmology must explain growth. Because of this affinity between knower and known, it is my belief that science is coming not unlike the age of puberty, where its old and purely materialistic conceptions will no longer suffice. Indeed, the question that everybody is now asking in metaphysics, in the theory of reasoning, in psychology, in general history, in the history of languages, in sociology, in astronomy, perhaps even in molecular physics, is the question how things grow. And by far the most interesting aspect of the history of science is that it shows how an important department of human thought has been developed from generation to generation with the view of comparing this growth with the historical development of art, of religion, of politics, and of institutions generally, and not only with historical development, but also with the growth of the individual mind, and not only of mind, but of organisms, both in their geological succession and in their individual development, and with the formation of worlds, and even the gradual coming into being and crystallization of the fundamental laws of matter and of mind. From all of which facts taken together, we are to expect in the future a grand cosmogony or philosophy of creation. Now, growth appears to violate the law of energy. To explain it, we must at least suppose a simulated or quasi-chance, such as Darwin calls in to produce his fortuitous variations from strict heredity, which we now call random genetic mutations. Whether the part played by natural selection and the survival of the fittest in the production of the species be large or small, a very remarkable feature of Darwinian theory is that it shows how merely fortuitous variations of individuals together with merely fortuitous mishaps to them would, under the action of heredity, result not in mere irregularity, nor even in statistical constancy, but in continual and indefinite progress toward a better adaptation of means to ends. How can this be? There are just three factors in the process of natural selection. To wit, first, the principle of accidental individual variation or random mutation. Second, the principle of hereditary transmission, which wars against the first principle. And third, the principle of the elimination of unfavorable characters. The principle of accidental individual variation is the principle of irregularity, indeterminacy, chance. It corresponds with the irregular and manifold wandering of particles in the active state of the protoplasm, It is the beginning in of something fresh, the bringing in of something fresh and first. Darwin's theory depends on the reality of chance events, so we should adjust our cosmology away from determinism. I thus argue in favor of a way of thinking, which it will be convenient to christen tychism, the Greek word for chance. I believe that tychism must give birth to an evolutionary cosmology in which all the regularities of nature and of mind are regarded as products of growth. Such are the materials out of which a chiefly philosophical theory ought to be built in order to represent the state of knowledge to which the 19th century after Darwin has brought us. Here is how the universe began. Like some of the most ancient and some of the most recent speculations, such an account of the universe as a whole would suppose that, in the beginning, infinitely remote, there was a chaos of unpersonalized feeling, which being without connection or irregularity would properly be without existence. This feeling, sporting here and there in pure arbitrariness, would have started the germ of a generalizing tendency. Its other sportings would be evanescent, but this would have a growing virtue. Thus, the tendency of habit would be started, and from this, with the other principles of evolution, all the regularities of the universe would be evolved. At any time, however, an element of pure chance survives and will remain until the world becomes an absolutely perfect, rational, and symmetrical system in which mind is at last crystallized in the infinitely distant future. According to this view of the universe, uniformities are never absolutely exact, so that the variety of the universe is forever increasing. At the same time, even these departures from law are subject to a certain law of probability, and that in the present state of the universe, they are far too small to be detected by our observations. Chance and habit taking can explain why the laws of physics are the way they are. I adopt this hypothesis as the only possible escape from making the laws of nature monstrous arbitrary elements. Among the things that demand explanation, then, are the laws of physics, and not this law or that law, but every single law. Why are the three laws of mechanics as they are and not otherwise? What is the cause of the restriction of extended bodies to 3 dimensions? And then the general fact that there are laws. How is that to be explained? We wish to make the laws themselves subject to law. For that purpose, that law of laws must be a law capable of developing itself. Now, the only conceivable law of which that is true is an evolutionary law. It is therefore reasonable to suppose that all law is the result of evolution, and to suppose this is to suppose it to be imperfect. Errors are thus part of the cosmos. My proposed law of laws accounts for the main features of the universe as we know it, the characters of time, space, matter, force, gravitation, electricity, etc. It predicts many more things which new observations can alone bring to the test. May some future student go over this ground again and have the leisure to give his results to the world, which, my friends, we've done with software Peirce could not have imagined. This evolutionary cosmology fits with Darwinian theory, but it also adds growth by love, in addition to growth by natural selection. The theory of Darwin was that evolution has been brought about by the action of 2 factors. First, heredity, as a principle making offspring nearly resemble their parents, while yet giving room for accidental variations, for very slight variations often, for wider ones rarely. And second, the destruction of breeds or races that are unable to keep the birth rate up to the death rate. The vast majority of our contemporary naturalists thus hold the opinion that the true cause of those exquisite and marvelous adaptations of nature is that creatures are so crowded together that those of them that happen to have the slightest advantage force the less, pushing them into situations unfavorable to multiplication or even killing them before they reach the age of reproduction. Much is to be said for this competitive view. However, I could not conceal my own passionate predilection that love is also a driving force in the universe. Suppose, for example, that I have an idea that interests me. It is my creation. It is my creature. It is a little person. I love it, and I will sink myself into perfecting it. It is not by dealing out cold justice to the circle of my ideas that I can make them grow, but by cherishing and tending them as I would the flowers in my garden. Such growth is not driven by chance or mechanical necessity, but by love. Such a confession will probably shock my scientific colleagues. Yet the strong feeling that the theory is attractive is in itself, I think, an argument of some weight in favor of the agapastic or love-based theory of evolution, so far as it may be presumed to bespeak the normal judgment of a sensible heart. Certainly, if it were possible to believe in agapasm without believing it warmly, that fact would be an argument against the truth of the doctrine. At any rate, since the warmth of feeling exists, it should on every account be candidly confessed. I'll go back at this at the end. So to summarize, here are the basic forces of the universe. 3 modes of evolution have thus been brought before us: evolution by fortuitous variation, evolution by mechanical necessity, and evolution by creative love. We may term them tykastic evolution or tykasm, anankastic evolution or anankasm, and agapastic evolution or agapasm. According to this cosmology, 3 elements are active in the world. First, chance. Second, law. And third, habit taking. This account of the universe yields the following picture. Uniformities in the modes of action of things have come about by their taking habits. At present, the course of events is approximately determined by law. In the past, that approximation was less perfect. In the future, it will be more perfect. The tendency to obey laws has always been and always will be growing. We look back toward a point in the infinitely distant past when there was no law but mere indeterminacy. We look forward to a point in the infinitely distant future when there will be no indeterminacy or chance but a complete reign of law. But at any assignable date in the past, however early, there was already some tendency toward uniformity. And at any assignable date in the future, there will be some slight aberrancy from law. Moreover, all things have a tendency to take habits. From atoms and their parts, molecules and groups of molecules, and in short, every conceivable real object, there is a greater possibility of acting as on the former like occasion than otherwise. That's basically the law of laws I stated. This tendency itself constitutes a regularity and is continually on the increase. In looking back into the past, we are looking toward periods when it was a less and less decided tendency. But its own essential nature is to grow. It is a generalizing tendency. It causes actions in the future to follow some generalization of past actions. And this tendency is itself something capable of similar generations, and thus it is self-generative. We have therefore only to suppose the smallest spore of chance in the past, and that germ would have been bound to develop into a mighty and overruling principle until it supersedes itself by strengthening habits into absolute laws, regulating the action of all things in every respect in the indefinite future. In formulating how, I know, I'm having goosebumps. In formulating how the laws of physics came about, I'm trying to avoid the hypothesis that this or that is inexplicable. For the only possible justification for so much as entertaining a hypothesis is that it affords an explanation of the phenomenon. Now, to suppose a thing inexplicable is not only to fail to explain it, and so to make an unjustifiable hypothesis, but much worse, it is to set up a barrier across the road of science and to forbid all attempts to understand the phenomenon. Shockingly, my friends, matter is not the fundamental stuff of the universe. Someone who takes this approach, for example, would never be satisfied with the hypothesis that matter is composed of atoms, all spherical and exactly alike. If this is the only hypothesis that the mathematicians are as of yet in condition to handle, it may be supposed that it may have features of resemblance with the truth, but neither the eternity of the atoms nor their precise resemblance is even admissible hypothetically, for that would be to attempt to explain the phenomena by means of an absolute inexplicability. This materialistic doctrine seems to me quite as repugnant to scientific logic as to common sense, since it requires us to suppose that a certain kind of mechanism will feel, which would be a hypothesis absolutely irreducible to reason, an ultimate inexplicable regularity, while the only possible justification of any theory is that it should make things clear and reasonable. Why should matter turn around and start saying, I love you, or I feel pain? Since we must not admit mysterious discontinuities, we must accept that matter is proto-conscious and proto-alive, just really undeveloped. The one intelligible theory of the universe is that matter is effete or very ineffective mind, invertebrate habits becoming physical laws. This obliges me to say, as I do say on other grounds, that what we call matter is not completely dead, but is merely mind hidebound with habits. It still retains the element of diversification, and in that diversification, there is life. The life slimes or protoplasms have the peculiar property of growing. Crystals grow. Their growth, however, consists merely in attracting matter like their own from the circumambient fluid. Each slime in its growth preserves its distinctive characters, with nerve slime growing nerve slime, and muscle slime muscle slime, lion slime growing lion slime, and all the varieties of breeds and even individual characters being preserved in the growth. The frequent liquefaction of protoplasm increases its power of assimilating food, and so much so indeed that it is questionable whether in the solid form it possesses this power. The life slime wastes as well as grows, and this too takes place chiefly, if not exclusively in its liquid phases. Closely connected with growth is reproduction, and though in higher forms this is a specialized function, it is universally true that wherever there is protoplasm, there will be, or has been a power of, reproducing the same kind of protoplasm in a separated organism. Reproduction seems to involve the union of two sexes, though it is not demonstrable that this is always requisite. Another physical property of protoplasm is that of taking habits. The course which the spread of liquefaction has taken in the past is rendered thereby more likely to be taken in the future, although there is now no absolute certainty that the same path will be followed again. Very extraordinary, certainly, are all the properties of protoplasm, as extraordinary as indubitable. But the one which has next to be mentioned, while equally undeniable, is infinitely more wonderful. It is that protoplasm feels. We have no direct evidence that this is true of protoplasm universally, and certainly some kinds feel far more than others. But there is a fair analogical inference that all protoplasm feels. It not only feels, but exercises all the functions of mind. I argue for this continuity between the living and the proto-living, and between the conscious and the proto-conscious, out of a commitment to cynicism, which is a tendency of philosophical thought which insists upon the idea of continuity as of prime importance. The three semiotic categories are the best way to understand not just all experience, but all of reality. If, as I have argued, the standard deterministic materialist worldview is wrong, what shall we replace it with? Grant me that the three categories of firstness, secondness, thirdness, or quality, reaction, and representation have in truth the enormous importance for thought that I attribute to them, and it would seem that no division of theories of metaphysics could surpass in importance a division based upon the consideration of what ones of the three categories, each of the different metaphysical systems, has fully admitted as real constituents of nature. There will then be 7 possible cases: 1, 2, 3, 1, 1, 2, just 3, 2 and 3, and so on. Nihilism, strict individualism, Hegelianism, Cartesianism, Berkeleyanism, ordinary nominalism, and finally the metaphysics that recognizes all the categories. I hold the last view, that all the three categories are real. Looking at thirdness, it seems a strange thing when one comes to ponder over it, that a sign should leave its interpreter to supply a part of its meaning. But the explanation of the phenomenon lies in the fact that the entire universe, not merely the universe of existence, but all that wider universe, embracing the universe of existence as a part, the universe which we're all accustomed to refer to as the truth, that all this universe is perfused with signs, if it is not composed exclusively of signs. The end. I'm going to answer some questions, but right now, what did you think of this mind trip? We're ending. I put this at the end of the class. My friends, what did you think? I'm gonna let you tell me what you thought. Yeah. You definitely need rereads, that's for sure. And I have to say, it took me decades to start understanding what the heck Peirce was talking about and to start seeing that he might be right. Like literally teaching is the best way to understand, right? And Andrew, there's a sense in which he does, and we did in this class. Do you see that? And the evidence for this stuff, one of the things that, for instance, Peirce says that might cause you pause, for instance, let's just take one thing. So I'm going to just answer Ariana's question first, right? You can go over this. It's in the reading, the different isms he gives to these views here, right? Nihilism is just basic firstness, right? There's only firstness, right? There's only firstness. That's what it is. So it's just like, it's just pure chaos and always pure chaos. Do you see that, Ariana? It's only firstness, and there was never any, the grounds for something that developing into order was never there. It's like every time you drop a effing rock, it's always, each time, anything can happen. Every time. Chaos. Parmenidean flux. Yeah. Yeah, well, that's the thing, right? He's going to say that if that chaos, if you couple, like let's go back just 1 second, right? Think about this for a moment. If you just have a situation, let's say, right, where we have this, let's go back to our hand, and anything can happen, just anything can happen, but you don't have this law, which is the law of habit taking. Okay, so on one occasion, the rock goes here. On the second occasion, where's it going to go? Let's say first occasion it drops. Second occasion, where's it going to go? The first occasion it went here. On the second time you drop it, where's it going to go? Pure chaos, let's say. There's no this. Take this out of the equation. Let it make it pure chance. It went here on the first occasion. Second occasion, where's it going to go? Wherever. It went here. Third occasion, where's it going to go? Again, wherever. Each time, you never know. That would be nihilism in the sense of which he talks. It'd always be perpetual firstness. We'd always be here. Anything can happen. And we never have the grounds to move beyond that. What you end up with is something like this, right? What you end up with is anything can happen, right? Anything can happen. Anything can happen. That's it. That's not what he's advocating, right? Because for him, what you have in addition is not just chance, because notice here what I said we would use as our ingredients to build our universe, but chance and habit taking. And habit taking is captured by this law of laws. Once you throw habit taking in the mix, then anything can happen will start growing into a regularity. But when you have his 7 systems of metaphysics, a classification into 7 systems of metaphysics, this here, just one, that's just pure firstness, pure potentiality, pure spontaneity. Yeah. Ariana, do you see that? No one obviously believes in that. I like what you wrote. No one really believes in that, right? Because the world has some regularity. And notice you don't have to have perfect regularity to admit that there's some regularity. And Peirce is somewhere between, he's not a clockwork universe, right? But he's not like that anything goes universe either, right? We're somewhere in between those two. We're somewhere in between those two. And we're moving towards greater regularity, but because regularity just tends to reproduce itself. That's it. And it reproduces itself based on different fundamental forces, chance, habit-taking, law, and he talks about love as well, right? Being pulled, being developed out of something else that's not reducible to mechanical necessity or chance or competition, right? So one of the forces that took me the longest time to see and to understand and to see in a charitable light was the agapasticism story, the story of love, this evolutionary love story, right? And if you want, I could tell you a little bit about that more, but folks are typing and I'll see what folks are typing. And then we'll slowly, because that was it, right? Owen says, this is so hard to fathom for me because I can't even believe there's another way to think on these topics, but he justifies it so well. And I think he does, right? You can test for this. One of the reasons why people like Lee Smolin that you just saw think that Peirce is, they look to Peirce so much is because if you do keep investigating this, and again, the truth will reveal itself over time, not just in 1 hour. Keep investigating, right? You'll see that that's not completely nuts. He's onto something, right? And it took me a while. The last thing of his cosmology that took me a while to understand was the evolutionary love stuff, right? Growth by love, that's the one that took me the last. Chance also, I had a hard time. I remember when I was first exposed to this, because I grew up like all of you in a Cartesian world of billiard balls hitting each other. That's the story I was told. The clockwork world, that's the one I was raised in, right? but it took me a while to kind of retool and to at least see it from that perspective. Andrew writes, but what evidence do we have that anything can happen and a dice roll can occur? Well, I mean, it comes down to this. Look at the predictions of anything except a toy model, Andrew, in any science you want. You always have to round out the results. That's your evidence. There are no frictionless surfaces. There's always something that you have to round out. You have to say ceteris paribus, all other things being equal. There's nothing in any science that's perfect in that sense. Every measurement, empirical measurement, when the rubber hits the road, not in the vacuum of theorizing, but when an astronomer or physicist or anybody else, let alone a social scientist, makes a prediction about the world and then goes to test it against observation, that observation is always going to have an element of not quite in there. That leaves room for the not quite. And it's not quite in principle because we don't have a theory of everything that explains and predicts everything. We can't even predict the weather. It's just a faith that tells us that, oh, yes, we can predict it. We're just short on knowledge. Peirce wants to own up to that. No, you can't predict it on principle, not just as a result of a shortcoming. That's his argument. There's an element of unpredictability in nature itself. It's not just that, oh, if I only knew more, I could predict the markets perfectly, right? There's an element of unpredictability. And one of the philosophers of science who was influenced by Peirce, Karl Popper, he always said, look, think about this for a second. Sit down and think about this for just 1 second. You're telling me that if you knew the temperature and the distribution of, let's say, helium 1 microsecond or nanosecond into the Big Bang, that you could predict the 71st note of, let's say, Beethoven's 8th concerto? Really? What in the world makes you think that that's true? That's an article of faith. That's just an article of faith. We have no evidence for that whatsoever. And in fact, the real evidence that we have is that we can't figure stuff out and predict it with the kind of certainty that the clockwork story can tell. So if you go back over the video, the whole story that you can predict the dice perfectly, right? Even though there are technically forces acting upon it from distant parts of the universe, he even acknowledged. That's just an article of faith. And Peirce is going to say, it actually, if you want to infer to the best explanation, is not the best explanation. So if you're comparing apples pairwise, this story is a better apple. That's what he's going to say. Andrew, does that make sense? And you get that article of faith a lot. Like it's one that a lot of philosophers are and scientists are married to, like a dogma, right? But Peirce bakes into his universe the error itself. Yeah. What evidence do we have that anything can happen that when a dice can roll? Look, really easily. Remember that moment in the video. Andrew, pause for a second. Remember the moment in the video when the person said, including forces acting from anywhere in the universe. Remember that? Right? There's something there, right? And then the article of faith is always that, oh, if we knew it all, we just don't. And the question is it just a temporary don't because we don't have all the knowledge? If we had a God's eye view on everything, we would. And the question is, let me put this in argumentative term. What has the onus of proof? The deterministic view or the indeterministic view? Not so much what's the proof. What has the onus of proof? What has to be justified? Does determinism get a free pass and indeterminism have to justify itself? Or is indeterminism in the default position and the onus of proof is on determinism? That's the best argument. The rest is, let's work this out over time, right? He doesn't claim to have a settled argument. He calls on future generations to keep working this out, right? But that's the idea. He's just switching the onus of proof. He says, look, I'm a scientist. I've actually done the measurements. They're not the way you'd like to think they are. Yeah. They both need to be justified, but the question is, which does the best job of justifying it? And in 25 years, you probably see that's just not crazy. Or so Peirce surmises. And then you put that to the test. Keep inquiring and you see if you converge towards his. Like everything else we did in this class. Does that make sense? That's all he ultimately says. It literally says, you go back in the reading, right? He says you put this to the test. And the test is going to be playing itself out. And you don't want to just account for one theory. So not just for the dice. You want to account for everything. It's a cosmology. So the dice is what Lee Smolin was talking about as a system compared to other systems. Fair enough. But why the whole, the universe as a whole? Why should it get a free pass? How do you explain that? You understand? You can certainly say that system is perfectly predictable in reference to another system. But then you take the system of all systems. Why that? And you ask that big why. And you then can't just speak as an article of faith that, you know, it's a certain way. You have to argue for that. And Peirce digs really, really deep into the bottom and does this fundamental cosmological reflection. And that's where he's going. And the rest, he's like, you figure it out. And then he dies. And he's like, you figure it out. Hey, again, you'd have to be a cosmologist to really assess all of this, right? Or a metaphysician. I'm a metaphysician, not a scientific cosmologist, but our tasks unite, right? They meet at some point. Like metaphysics and cosmology at some point touch each other, right? And you have to work on this stuff. It's just completely wild. What I've given you today is, at least for the some parts, the best story I could give you, and I hope you enjoyed it. My friends, was this fun? As always, clarity is not to be obtained within an hour or 2 hours in Peirce's theory, right? It's something to be happening over the long run, over a community of inquirers. You might not get the clarity in your lifetime. Your children might. They might grow up in a world where this makes sense. This is yeah. And I busted my butt really hard for this one, precisely because it's just so difficult for me. Yeah. I'm so sad now as well. I'm fixed with. All right, and I'm going to go for the agapasticism now. All right. I'm going to go for agapasticism. Peirce says, he talks about growth by love. And I'm going to end, actually, I'm improvising here. This is not scripted. But I'm going to end on this. I have children, you probably heard them, and I love them. Let's say if I have, if there's one little grain of bismuth somewhere on the earth, let's say somewhere in Iowa, there's a little rock of bismuth, and it turns out it's the only little block of bismuth in all of the universe. Must bismuth, which is a chemical element, must it be countenanced as one of the fundamental elements in the universe? Like there's a little grain, it's very small quantity. It's not like rock, there's not like a ton. There's a little bit of it in Iowa, just a little bit, right? Must we say it exists? Yes or no? Bismuth exists. Like there's a little rock of it. Yeah, of course we must, right? It doesn't matter if there's lots of it or if there's some on other world. If there's none, it doesn't exist. But if there are some, it exists, right? I'm going to give you a weird argument. I love my children. And my love for them is of the manner that Peirce describes. I want to see them grow. Now notice, I did my job. I've reproduced. And you could say for evolutionary reasons, I want to procreate the species. But you don't understand. When I want to see my children grow, I'm doing it because I'm pulled, not because I'm pushed. I'm doing it not on the basis of some Darwinian agenda. I love seeing them grow. I want to see them grow. I'm driven by not competition, not mechanical necessity, not chance, but by love. That suffices to say, if I'm right, and I, A, do love my children, and B, don't love them in a way that's reducible to chance, necessity, evolutionary pressures, and whatnot, that there's an element of love. I'm going to write this. There's an element of love in the universe. My mere loving them and that growth being fueled by my love is sufficient evidence for agapasticism being operative in the universe. Now it's going to channel back into this class. I love seeing you grow. And I love seeing this course grow. And I work my ass off to make it grow out of love. I don't get a better paycheck. It doesn't make me feed my family better. And my offspring are no more or better off. The food on the table is the same if I make a botched class or if I do it well. But I love doing a good lecture. And I do it out of love. I'm pulled towards this. I love knowing that the lecture and the course grew, that I nurtured it. And I love seeing that it's going to impregnate your minds and you're going to grow too. And I love the fact that you're going to grow. And if that's true, Peirce says, then love is part of the universe. And that's it. That's the happy note I'm going to tell you. I don't know if that made any sense. Sorry, that came from a very special place. Because it's hard. And I ain't doing this for the paycheck. I'm doing this for some other motive. Right? And it only takes one speck to say it exists. And if you love someone too, and if you love something, some idea, if you are in love with something, Peirce says, remember phaneroscopy. You have to admit, you have to be honest, you have to admit what presents itself. That's part of the universe. It has to be, it's a driving force for why you want to see your relationship grow, why you want to see your book published, why you want to see your muscles grow when you work out. You have a project, right? Oh, and I don't want to be online because I'm too crazy. People think I'm nuts. But if you've ever nurtured something and let it grow, I invite you to meditate on what's going on and to keep an open mind and to think about what Peirce said about agapasticism and how the universe might not be this barren place after all. It might be quite meaningful. It might be teeming with meaning. The signs might be baked into it, and different forces of chance and surprise and love and wonder might be baked into the world. My friends, that's the note on which I can't go any wilder than this. Otherwise, I'll be bloody, Deepak Chopra or something. So I got to stop here, right? Because then I'm still a philosopher, right? So that's as far as I can go. That ends the class, my friends. Study and prep for the final exam. And holy cow, good luck for the exam, and thank you for being such great students. I love you, and in the strictest sense, I was glad to have this period with you, which I'll never have again. Thank you, my friends. Thank you. I really appreciate all of you. This is an individual thank you, not just to a group. Each one of you, Arjun, Ariana, Reese, Stephen, Chiamaka, Vera, Chahong, Nav, all of you, Andrew, Curtis, I really, Julia, man, I was so happy you were in for the ride. Ritu, Hannah, thank you so much. Owen, go kick some ass in that exam, all right? Let's make it happen. Yeah, well, if it was in person, you'd probably see them. Yeah, it's still a lot of energy. Sweta, I was so happy to have you along for the ride. This was such a fun ride. Vera, thank you so much. You folks, and keep it up. Keep investigating. Keep being interested in philosophy. John, Nav, all of you, thank you so much. Let's. I'm going to stick around if anyone wants to discuss ideas a bit more. If you need some help with anything, at this point, I'm not going to be the sharpest tool in the shed because I'm completely burnt out. But I'll give you every last drop I have, and I'll be the last one to leave the room. Other than that, we say goodbye and good luck for the final. Oof, I'm so glad I'm done. Take care, John. Bye, Reese. It's physically the man. I'm just gonna. Thanks for everything, Andrew. Thanks for you as well. Keep inquiring. Keep being critical. Keep poking away. Thanks, Andrew, and thanks for your passion as well. It's in the overlap of both of our passions that the Venn diagram comes alive.